Today's plan is to talk about what's called Kac-Moody Lie algebras. It's a natural thing if you try to invent something infinite dimensional, but which behaves like inherits a lot of stuff that we learned before. So we start with definition. Let A be a square matrix n by n with just complex entries. A realization of A is the following data. So it's a triple. You have some objects h, pi, and pi check inside. So this is a vector space. So where h is finite dimensional vector space. Pi, okay, I should start maybe with pi check for some reason. So it is some subset consisting of n elements inside H. It is, and these vectors in H are linearly independent. Subset. And I would like to stress that this might not be a basis. So they are linearly independent, but you might have less than h's than needed for a basis. So n might be less than dimension of h. I should write it like this, right? And then pi, it's also a bunch of elements, but they are inside H star, so dual to H. And this is and alphas are also linearly independent. So linearly, again, linearly independent subset. And okay, we also, so far no connection with A, right? So we need some connection, so such that alpha I of Hj is A Ji. So now it's all kind of, you know, you can see the motivation for such definitions, right? Because you know now everything about simple Lie algebras, right? Okay, so this is the end definition. So such data we call realization of A. Let's prove first lemma. So if h pi check is a realization of A, then we know we have some relation. So dimension of H cannot be less than 2n minus rank of A. So let's prove this. So what's going on? So let me just introduce short notation for rank. It's R, and short notation for dimension of H is M. All right. And we would like to extend pi and pi check to the bases alpha 1, alpha m, and h1, hm of h star and h respectively. So m might be greater than n, as I pointed out. Then let me consider a matrix alpha j hi. So ijth element is alpha j hi. So ij here runs from 1 to n, m. This matrix has blocks, and here in the left upper corner you have A, and then some other blocks B, C, D. But what's important here is the A that we started with. Okay, so and of course it is inversible because now alpha j and hi are bases in h star and h respectively. So it's inversible. In particular, any subset of rows that I take here are linearly independent. Right? So I would like to take first n rows, and this will be a matrix which is not square, but m by n, and it has rank n because right, because it has n rows. So this implies that this has rank n. Okay, but this has rank n means that I have n linearly independent columns in this matrix, right? So let me choose these columns. So therefore, we can choose n linearly independent columns in this, and once we choose them, some of them are in A and some in B, right? So n1 is columns linearly independent columns that I choose on this step in A, and these are linearly independent columns in B. But A has rank R, right? So I just denoted it by R. So therefore, n1 smaller or equal than rank A, which is R, and so and n2 smaller or equal than rank B. Right? Just because of definition of rank. So therefore, I can say that, okay, n is smaller than rank B plus R. So therefore, rank B is greater or equal than n minus r, but rank B is B is what? It is n by n minus m matrix, right? And by m minus n, right? This m minus n by n. And of course, rank B cannot be bigger than number of columns, right? So therefore, I have this, right? So therefore, m minus n is greater or equal than n minus r. So therefore, I have m is greater or equal than 2n minus r. This is exactly what we needed. M was dimension of H, 2n minus r. So we proved. Okay. All right. So since I have this lower bound, let me choose. Let me see if I can achieve equality there. And if I can, such a realization I will call a minimal realization. So definition: if dimension of H equals to n minus rank A, then realization H pi check is called minimal. Let's see if there exists a one. So proposition is that the answer for this is yes. Any square matrix has minimal realization. Proof. So okay, let me again fix the matrix. A, it's n by n with complex entries. And suppose that R is rank of A. Then let me maybe after rearranging rows and columns, A will have the following form: A11, it's blocks again, A12, A21, A22. All right, and this one is R by R matrix, and a determinant where determinant of A11 is not 0. Okay, so and I can rearrange rows and columns because because if I obtain the realization for A, which is rearranged, then I obtain the realization for A because it's just renumbering of elements of pi and pi check. Okay, so I can do this, and just simpler to show on the board that my matrix, which with R by R matrix, whose determinant is not 0, is here. Yes, so it's like a It's exactly the rank of A, yes. All right, so then I define another matrix, C, which is this. Okay, in the upper corner I have, again, A, that I would like to present as corresponding blocks here. And then I have additional blocks, so it's bigger. I have 0 here, identity matrix of size n minus r here, 0 here, identity matrix of size n minus r here, because this one is n minus r times n minus r, and 0 here. So this is a matrix of which size? So this is matrix of size 2n minus r times 2n minus r. Okay, and then I claim the determinant of C, of this matrix of C, is actually not 0. And you can see, for example, you can start, expanding the determinant from using this column and then this column and this column. You'll see the determinant of this is plus or minus the determinant of A11, actually. Okay, because you will cross out all these rows when you compute determinants, and sign is because you have not the first position here. Anyways, but what's important is non-zero. In particular, and we can now use this matrix to take our h's and alphas. So take h1, hn to be the first n rows of C. Right, so I actually identify H. So I just take H to be what? C 2n minus r, right? And take like a standard basis there. And with this standard basis, vectors in H are identified with rows of some matrix. So I take H1, Hn to be the first n rows of C. So since C has determinant non-zero, they are all linearly independent. Okay, and then it's clear what should be alpha 1. So and alpha i's, and take alpha 1, alpha n, this will live in C 2n minus r like star, right? In H star. So I just define this to be like the first n elements of the basis which is dual to the standard basis. So just alpha I of Ej is delta Ij. Then therefore, if alpha I is so if alpha I is H J, then it will be corresponding entry of Cartan matrix, and this will be realization. Okay. So this here E1, E2n minus r standard basis of C to n minus r. And so these are, of course, linear independent. These are linearly independent. Alpha I of hj is an element of Cartan matrix as we need, right? And that's it. So this is and dimension of h is exactly to n minus r. So this is a minimum realization. We just constructed it. Okay. And we proved proposition. Okay, so now idea of constructing Kac-Moody Lie algebras is just, okay, so in simple Lie algebras we actually have simple Lie algebra, right? And then we have corresponding Cartan matrix. Now let's try to take just some arbitrary matrix and try to construct some Lie algebra along, you know, and this construction should look like what we had in simple Lie algebras, okay? But of course, if you take any matrix, you cannot guarantee that you'll get something good. At least like the cell relations that should make sense, all right? And at least so we would like to have some, you know, and some relations similar to cell relations, which will be called cell relations in this case as well. So what are the most general class of matrices that we can take? So these are called generalized Cartan matrices. So definition, a matrix n by n again is called a generalized Cartan matrix if the following conditions are satisfied. First of all diagonal entries I would like to have 2. Okay, so I from 1 to n. Second, I would like aij to be less or equal to 0 if I is not equal to j. And third is that I would like to have aij equals to 0 if and only if aji equals to 0. So these are 3 conditions that I would like to have. So why these 3 conditions are I must have? Because, so this one is because I would like to have SL2 triples in my Kac-Moody Lie algebra. So if you remember cell relations, so this 2 was very crucial there. Okay, so I would like, and my SL2 triples was one of the most important instrument like in everything there. Okay, so this 2 is very important. So aij less or equal than 0 is just because, remember we had at ei ej 1 minus aij, such thing. So this is some power of an operator, okay? And if this power is negative, then you don't know what to do. So we actually would like to have something like this, okay? And this one is also because of the following, of the same reason. So if aij is 0, it means that ei ej commutes, right? And like in cell relations, right? So, but it means that ej with ei commutes as well. So this condition also is natural. Okay, but so far we don't have any relations. I'm just motivating these 3 conditions. All right. Okay, so next step is to introduce some algebra. So okay, let A be a generalized Cartan matrix. H pi check minimal realization of A. Okay. Right. Then let L of A tilde be the Lie algebra defined as follows. So X. With generators, so it has generators. We define it by generators and relations. Generators is the following set: E1, En, F1, Fn. All right, where n is the size of Cartan matrix. A is again matrix n by n. And H, and H might be of different dimension than n. Okay, which was different actually in simple Lie algebras. H was also has dimension, the same dimension as n. So actually I should say here different. So I take all x tilde, so I label generator somehow. Okay, and so I have these generators, so it just names or labels for generators, and x tilde as x runs over h. Okay, so this is the whole set of my generators, and relations that I put on them. First of all, so far it is a set, right? But I really would like this to be everything which is given by x tilde as x in H will be isomorphic to H, right?
This set is a basis of H?
No, not. It's just every element. So I have actually like. Technically, I have infinite number of generators here, right? So 2n of E and F's, and every vector is just different element. So far, it's just different element of my Lie algebra L tilde of A. Okay. But now I'm giving. Who is infinite dimensional?
If the whole space, the Lie algebra you are constructing is infinite dimensional, then
It's just the same. It's just the same. So all words, all finite words in. It's just you can have, for example, word of. So your question is about what is a free Lie algebra. On an infinite set, right? Yeah. So this is your question. So it's just the same as no difference with finite set. It's just, for example, if you consider word like Lie words, right? All these things with brackets of length 1, you'll have infinite number of them. For example, it's just the only difference, but you still have all that. Right? It's all finite words, but in an infinite alphabet. Still.
Any
Yes, yes. So finite words in infinite alphabet. Still, you can do this. But all this is just a technical thing. Of course, it's good to ask yourself these questions, but because now I give you a relation that says that, okay, x tilde is lambda y tilde plus mu z tilde for each x, y, z in H such that x is lambda y plus mu z. So this is all technical because of course I have H1, H2, and so on, Hn, right? As I had in simple algebras. But it's not the whole H now. So how I generate? I don't know. I don't have now. I didn't specify the completion to the basis of H, right? So that's why I need this technical thing, right? So.
Why do you say that all the H1 to Hn are not all of H?
Because a dimension of H might be bigger than dimension of n.
Okay,
So even in minimal realization, dimension of H, let us recall, is 2n minus r. So we'll have for the next time we'll consider our main example will be this one, 2 negative 2 2. So this is a finally algebra SL2. And then so dimension of H here is 3. It's 2 times 2 minus, and rank is 1. Right? So you have 2 E's and 2 H's, but the dimension of H is 3. And to add, we didn't never choose like what else is there. We need this technical stuff.
Simple root and positive difference.
Say it again. Sorry.
It's like n is the dimension is the number of simple roots, and the dimension of H is the
No. You will have a lot of roots there.
positive.
You have an infinite number of roots actually. Yeah. Yeah. All right. So, but this will make H tilde, if you wish, right? All these elements to a vector subspace. So this condition, right? And then we have so of course we would like this to be an equivalent of Cartan subalgebra. So this should commute for any x and y and h, and EI with Fj is 0 if I is not equal to j, and EI Fj is h. So EI Fi is hi tilde, right? As I goes from 1 to n. So this HIs we have them. Then and then we have so actually I introduce everything except this complicated cell relation of the form at 1 minus Aij Ei equals to 0. I introduce everything except that. Okay, this is my L tilde of A. So x tilde EI equals alpha of x tilde EI. Sorry, which alpha I guess, right? Yes.
Sorry, I have a question.
Yes?
Your x tilde is a set, right? Is a subset of H.
So yes, before this condition it is. After applied this relation, it's already a vector space. Because I said, okay, if I have some relations in H coming from H being a vector space, let me have the same condition, let me have the same relation on H tilde.
So your Y tilde and Z tilde is in the set of X tilde?
Say it again, sorry?
Your element Y tilde and Z tilde is two elements, right?
Yes.
The question is, so what is the relation between X and X tilde?
Yes, so X is an element of H. It is a label of an element in L of A tilde. So for each X and H, I have an element X tilde in L of A tilde. Right? It's just how I construct. Right? So I have some infinite set, which is H. And each element of this set is labels and a generator. So that's what's written here. But then, of course, I would like them to behave actually like as a vector space. Like it's just the same. It's just this is just some technical stuff to add something from H that I don't that more than just a span of HIs. You see, without choosing some basis, additional basis. I don't need that.
So X tilde is like some element that has the index X.
Yes, if you wish. All right. Did I forget anything? Yes. And with Fi's, it is negative alpha I X tilde Fi. I from 1 to n here. I from 1 to n here. Okay.
You are preserving the same relations as in H?
Yes.
What is the difference between?
Difference. There's no difference. It's still there. It's just a technical thing. I mean, I cannot just take. So usually I take like a finite set of generators, right? And what I could write here, like in a simple Lie algebra, what do? I write H1, H2, and so on to Hn. If I introduce just them, it will not be enough. Because I have a bunch of other elements which are not in the span of H1 to Hn. But I would like to introduce all of H inside my L of A. So this is just some technical way how to do this, right? Without choosing like a completion of H1 to Hn to the basis of the whole H. Okay, it's just.
So your HI tilde is an element in your set X.
Yes.
Ah, okay.
Mm-hmm.
Sorry, one last question. You are writing this element that is not in H1 to Hn as X tilde?
No. H something with tilde it doesn't mean that it is not in the span of H1 Hn. It's just an element in H.
So, okay, I think we are trying to do this technicality because in the span of H1 to Hn is not all the H,
Yes.
right?
Yes.
So where is that element which is not all of H? No, which is all of H but is not in H1 to Hn?
So just take some element from X which is not in the span, and tilde of this element will be this.
Okay.
Yeah. Okay, so lemma 1. L tilde of A as a representation of H tilde. So H tilde is now vector space because of this relation, which is isomorphic to H, right? It's just H inside L tilde. And it is some commutative Lie algebra. Uh-huh.
Is this before we give this relation? Is it like the superposition in quantum mechanics?
I don't know.
It is just you just choose any point, be a new basis.
Yes, yes, you can think of. Yeah. But here I'm not choosing a basis though. I'm choosing
It's like
I'm choosing generators of Lie algebras. Yes. Well, which is yeah. You have a linear combinations of those as well, but also like a Lie words. And then before I introduce relation, of course, it's a huge thing. Yes. Okay. So H tilde is an abelian subalgebra of L tilde of A, right? Because of this relation, and it acts by a joint action, just by taking commutators. So L tilde of A, the representation of H tilde, admits a weight decomposition. Weight decomposition. So we have L of A. So what does it mean? L tilde of A is a sum L tilde alpha of A. Alpha runs over H star, where L alpha tilde of A, it's what you think it is. It's x of L of A such that so H x action of H on X gives you the multiplication by alpha of H of X for any H from H tilde. At some point, I will even forget that I put tildes in here, quietly, because because H and the H tilde now is isomorphic, so I can identify them in there. Okay. So is the statement clear? So we have weight decomposition. So actually root decomposition in this case. Okay. It is clear because because E, I, F, I, and H and X as X in H. So all the generators, they are weight vectors, right? If you try to commute some element of H with any of those, you'll get multiplication by number. Here multiplication by 0, here by alpha I, here by negative alpha I, right? So these are weight vectors. But then if you have some weight vector, so if you have W living in L alpha of A tilde, then for example you can commute with EI, right? And this is follows from commutation relations, and we did this computation many times. It's just in L alpha plus alpha I of A. So this is inside. So EI actually raises, so action by EI gives me a raise in the weight by alpha I. And with Fi and Hi, let me just so with Fi and X tilde, X in H is just similar computation. For Fi you'll have minus here, for H you'll have 0. And so therefore, if I try start with this and apply all the commutators, I get only weight vectors, right? But applying all the commutators, I get all the L tilde of A, just by definition. It's generated by all this stuff, by applying commutators. So starting with weight vectors, I generate everything obtaining weight vectors, so therefore I have weight decomposition. Okay, this one is pretty straightforward, but I need this for the following corollary. Any ideal L, maybe I, inside L tilde of A, admits weight decomposition. So any so this one is clear because so proof. Maybe let me just write a couple of words. So any ideal of L tilde of A is a submodule of H, right? Any ideal, right? If you try acting on H, it's invariant just because it's an ideal, right? And then we apply the problem from one of the seminars. So if you have commutative algebra, H tilde in our case, right? And a representation which is L tilde of A in our case, which admits weight decomposition, then every submodule admits weight decomposition. Okay? So L tilde of, so let me write it like this. I is an H tilde submodule of module L tilde of A, of H tilde module L tilde of A, that admits weight decomposition. Therefore, then apply problem. Maybe we can even remember. So it was in the last seminar. First from last seminar, I think. It's 11.1. Yeah, I think so. I even wrote it in my notes. From seminars. Okay. Okay. So then let us prove Lemma 2, which says that L tilde of A contains an ideal I such that its intersection with H tilde. So maybe at this point, let me stop writing H tilde. H and H tilde are the same thing. Okay, all are subalgebras in L tilde of A. So intersection is trivial. So contains an ideal such that intersection is trivial, and it's maximal with such property. And if J is another ideal such that j with h is 0, then j is contained in I. So L tilde of A has a maximal ideal among those which intersect with H trivially. Let's prove this. This one is just follows from Corollary. Okay, proof. So if I take some ideal such that it intersects with H trivially, then it's in its weight decomposition. Let me again use the notation that we had. So alpha is some elements of H star, right? Such that in this decomposition we have alpha is not 0. Okay. Right, because yeah, so if you consider weight decomposition of L tilde of A, J0, L0 is exactly H. L tilde 0 of A is exactly H. Okay. But intersection with H is trivial, so therefore it does not contain zero weight subspace inside. On the other hand, then we just take I, which is sum over all ideals, such that sum over all j such that its intersection with H is trivial. Then again, it is an ideal, and so then because in any of this ideal there's no zero weight subspace, then in the sum we will also have no zero weight subspace. Right? So therefore I intersects H trivially. And this is, I is the ideal that we need. It intersects H trivially, and it contains all other ideal that intersects H trivially. Okay, this and we obtained it using like a standard already for us trick. We have weight decomposition, and something is missing in this weight decomposition. So therefore, sum of everything also will have this piece missing. Okay, so that's the how it's done.
I have a question about this description of this lemma. You say if this satisfies this condition, then J is in I, right?
Yes.
Can we also just say I is also in J?
No.
What's the difference between?
No, I say that there's a very specific I, such that all so if you consider all ideals with this property, I claim that there is a maximal one. So I is the maximal one, and J is anything, any other in this setting. Okay. Yes. So therefore, I found this ideal I, and now I'm ready to define Kac-Moody Lie algebra. So you see, something was missing, like this hard relations, they were missing, right? Of course, we would like to, like simple Lie algebra, to be included in our generalization. So we would like to have something like relations. So instead of including them, and we will just quotient by this ideal I. Okay, definition. L of A, Lie algebra, L of A, which is a quotient of this by I, is called the Kac-Moody Lie algebra associated to generalized Cartan matrix A.
Question about this lemma. Is that possible I is equal to 0 space?
Yes.
No problem.
It will not be the case, but yeah, why not? We know that this is not the case because we would like to include more relations, right? So we have more to quotient by it, but.
I'm asking, is that possible I here be 0?
Okay.
And the answer is yes.
Yeah, technically, why not? Yes. So the logic is it can be, yes.
It would be like something abelian.
No. It will be a big, actually, ideal, but like in practice, like what you do.
Yeah, I mean if the algebra is abelian, then this
If it's abelian, or yeah, every ideal.
I will be the hosting.
because I understand like this I is it's like everything outside this like an analog of H. Before we have H plus
Yes.
this upper triangular and
Mm-hmm.
lower triangular.
Yes.
So this I is like the upper and the
No. So this I, you should think of I is everything which is generated by elements of the sort at EI, EJ, 1 minus AIJ. So it's just this additional relation that we forgot. Right? We're not constructing Fermat model, so we were quotienting by n plus or n minus when we constructed Fermat model, so we will not have time for that in this course. But it's actually similar to simple Lie algebras. So think of them as generated by this, and Fi of j is also. So the question is that really is this the same? If I just add these relations, do I have the same Lie algebra? Instead of quotienting, just add these relations. If it is the same LA or not. So the answer is yes, it is the same if A is what's called symmetrizable. It's can be presented as the product of diagonal times symmetric matrix. And this is a non-trivial result that we will not prove. But why do we even care and use this other definition? Because it's in practice it's much more simpler to check that something is Kac-Moody Lie algebra, or to check that some ideal is 0. Like when you're proving something, to check that some ideal is 0, you just need to check that it intersects trivially with H, or something like that. So of course you can check that your relation, like if you are given some algebra, you can check that these relations are true. That's okay. But how you can check that there are no more relations? This is very hard stuff. But with this definition, it's much easier to check that some Lie algebras are Kac-Moody Lie algebras. For example, we will see how to do that with affine SL2. Hopefully next time. Okay. Okay, from lemma whatever, lemma 1 we had. Okay, so from lemma 1, we also have that L of A also have root decomposition. So L of A admits also admits root decomposition. It is what? L of A is sum L alpha of A alpha. And let me actually decompose it like that. So let me separate H and then L alpha of A. So here it's alpha living in H star from minus 0. So I just separated H, which is L0, and everything else. Of course, we had this definition for L tilde. Without tilde, it's just the same, right? It's, H acts by multiplying by alpha of H. Okay, this is what's the L alpha. All right. So now we can define roots. Define roots. So R roots is all alphas from H star minus 0 such that L alpha of A is not 0. This is something familiar, right? Very natural. Think how to define it. Also, so this is then called root decomposition, and then we also can define reflections. So if I take some element, so I can define simple reflections. It is some linear map on H star, and it's defined like this: Si of some lambda is lambda minus lambda of Hi alpha I. So far, so before I defined reflections using form on H star R, right? So far I don't have any form. I can introduce it. It's one of the actually very important instruments in Kac-Moody Lie algebras, and we might be able to do this today. But this one is consistent with what we had, because this is 2 lambda alpha by alpha alpha if in our previous terms, right? But this one makes sense with all the in the generality that we introduced today. Okay, so I introduce some transformations Si. All right, and then I can define Weyl group now as everything which is generated by such things. So define the Weyl group as the group generated by Si, so I from 1 to n. Okay, so far we are kind of doing good, right? We can introduce a lot of stuff that we already had for simple algebras. The question is, can we now introduce positive, like polarization, positive and negative roots? So how? So of course you say, okay, I can. So R lives in H star, this finite-dimensional space. You can, draw some. Well, first of all, the problem might be that R is not finite now. So but still yeah. So you don't know. Maybe you can your plane that will intersect some roots. So you should be very accurate here. On the other hand, we already have simple roots. What should be simple roots? Pi, right? And remember that our polarization was very consistent with simple roots. So we cannot just, even if we could, introduce some plane that defines R to R plus and R minus, we should do it in a consistent way with pi, which is given to us as the minimal realization of A, right? We have finite simple roots, yes.
So this infinite maybe uncountably many.
Well, I don't know. I don't know for just any A. It's hard to say. Yes. Yeah, I think it's countable though, but there are Kac-Moody Lie algebras which are hard to treat. So I don't know. It's yeah. Something to be accurate. So I cannot claim like right away. So yeah. All right. But for, the idea how to introduce these roots is to like R plus and R minus is to introduce triangle decomposition first, and then this gives us actually R plus and R minus. So we're kind of moving backwards. So define n plus. It's a subalgebra generated by EIs. N minus, it's subalgebra. So again, subalgebra generated by FIs. So it's a words in EI and words in FIs, Lie words, right, with all these brackets. Proposition L of A is the direct sum of n minus plus H plus n plus. So what I'm actually saying is in this proposition, so far L of A is just any words. You can mix FIs, EIs, HIs, and do whatever you want, right? When generating stuff. But I'm saying that whatever, so all this is a linear compositions in like this, pure words in E's or in F's or H's. That's it. Right? So there's, you can always write this down as like a word in E only or in F only. So first of all, this sum is, so if I consider, okay, proof. So first of all, notice that n minus, so this sum is inside, and intersection of n minus and h, or n minus and n plus is 0. So therefore, this sum is direct. So this direct sum is inside. So we need to check that it's actually equals. Okay. Okay. So how to check it? So we'll use the following claim, which is obvious, but still. So let me say it like this. If a subalgebra some maybe L of A contains generators and is closed under the following undertaking adjoint action with EI or adjoint action with FI or at with X tilde as X runs through H. So if subalgebra contains generators and is closed under action of such operators, then it coincides with the whole L of A. Then L is L of A. So this one is clear because if you have a generators inside, right, and you start applying this at EI, at FI, like a lot of times, you'll get everything. L of A, right? Just by definition of L of A, right? But then you will never get out of L small because it's closed under the action of such things. So therefore, you generate the whole L of A, but never get out of L small. Therefore, L small should coincide with L of A. All right? Very well.
Closed and this mean something like the same relation?
No, closed means that if I take an element in L small, apply one of these, I'm still in L small. Invariant, yes, or yeah. So we need to check and okay. So generators are inside here, right? And F lives in here, lives in here, H is here. Very well. So I need to check that this thing is closed under taking of this. All right. We will. Again, I used this. So let me call an expression W. I don't know W. It's just a bunch of F's, right? Something like this. Yes.
You say L is a subalgebra, right?
Yes.
The subalgebra should be closed. Is closed with respect to what? Just.
No, it should be closed with respect to commuting two elements inside. Yes. Yes. Right. Sorry, you're right. Actually, I'm mistaken here. Should be not a subalgebra, but just a vector space, just a subset, if you wish, right? Is a vector subspace. So subalgebra is actually already closed, right? If you take EI and FI is already there, then I compute it's closed. Yes, very well. So it's a vector subspace Yeah, we never showed that this is subalgebra, actually. Well, if we show that, we are done, actually. Yes? So the objective is to show that this is subalgebra. Okay, we'll call such an expression a w.r.t in F1 Fn. I already used this terminology, so now let us fix it. And so if I have L of f's here, then I call it a word of length maybe I also indicate, so it's a length of W, L of W. So what I would like to see, so we will prove that add x of some word of 1 fn, right? So this is maybe some w of f1 fn. Lives inside H and direct sum and minus. And this is if for so this is x tilde for x, maybe just x, for x ei fi or x in H. So we will prove this by induction in L of W. So base is just easy, just check everything, right? At I, for example, of fj, so base is L equals to 1, right? So this is delta ij hi, right? So satisfies. At h fj is negative alpha of h fj, right? If h is inside h. And add fi fj is 0. So just these three formulas say that for L equals to 1, it is inside h plus n minus, right? H is in n minus, this is just 0, right? So base is L of W equals to 1. So L of 1 is just 1f. So I take just 1f everywhere. Okay, and step of induction. You just take your add x. So actually, each word in f's is a commutator of two other words. So this is my w, and this is for each w. It's like that, right? It's just take the the last bracket here. It's just commutator of two things, always. And these two things, are of the length smaller, strictly smaller than w. So L of W1 smaller than L of W, and L of W2 also smaller L of W. But then I just need to use Leibniz rule to write it's add x W1 commutator with W2 plus W1 add x W2. So this one lives in H plus n minus by induction assumption. And then this one lives in H plus n minus by induction assumption. But then, okay, so you have something from n minus times w2. So this is also in n minus. And then you commute h with w2, which is by induction assumption again in h plus n minus. Okay, and the same is here. So therefore, the whole thing is in h plus n minus. So that's it. So then I checked. So I finished the proof of proposition I claim, because okay, I checked this for words in F, for words in E or H similar, right? So therefore, if I apply it to n elements, if I apply these three things to elements of this subspace, I'm still in this subspace. So it's closed. So therefore, it's the whole L of A. Okay, and this thing is called triangular decomposition of Kac-Moody Lie algebra. Decomposition. And now we can define positive and negative roots. Just notice that actually n plus or n minus is sum over all L alpha of A. Well, where alpha lives in some specific subset R plus or respectively R minus that I'm going to introduce. Where R plus or minus is all alpha from R such that alpha is some ki alpha I from 1 to n, where ki is greater or equal than 0, or for minus less or equal than 0, for all I from 1 to n. It's just because you take E, right? It is just of weight alpha I, right? So it's in n plus, right? And then you start applying e's again to get n plus, right? But then when you apply e, you just add alpha i's, right? So everything in n plus, all roots that correspond to n plus will have decomposition to alpha i's with non-negative coefficients. And with n minus, it's just everything opposite with non-positive coefficients. And because of this decomposition, right, we know that n minus and h and n plus is everything. So because of triangular decomposition, the whole R is just a disjoint union of R plus and R minus, right? So this says, of course, can be defined regardless of if there's something else or not, right? But triangular decomposition says that there's nothing else. And yes. So of course we call R plus, so call R plus, and respectively R minus, positive or negative roots. Okay. Okay, so we have triangular decomposition. So let me introduce now where so far we have everything that we have in simple algebras, except that now W, so remark, W and R might be infinite sets. That was not the case before. But structure-wise, it's all kind of the same. We just need to to go backwards from Cartan matrix, more general form, backwards to get all the structures. Weyl group we have triangular decomposition, but then where all the magic happens is yes.
So you said might be infinite sets. Is there an example where it's actually an infinite dimensional algebra, but they are not infinite? They are?
No, so they are finite if and only if L of A is semi-simple algebra. Well, simple algebra.
Okay.
Well, semi-simple. I never said that A is indecomposable Cartan matrix. So yeah. Yeah. So actually, there's a classification of generalized Cartan matrices, and well, there are finite types, affine types, and indefinite types. So finite types are exactly semi-simple algebras. Affine types are affine Kac-Moody Lie algebras, which are like we're going to introduce. And indefinite type is just everything else. But finite type corresponds to finite W. Okay. So let me introduce something new that happens in here, except just finite and infinite. This thing. So actually, we now can consider. So definition alpha, root alpha is called real if alpha is obtained by an action of Weyl group on some alpha I. So for some W and W and alpha I from pi. Otherwise, alpha is called imaginary. And so the of simple roots, not transitively. So that's the whole thing here. So for semi-simple algebras, that was not the case. We could obtain all roots from simple ones by the action of Weyl group, and that was very important. Here it's not the case. We have some roots which are obtained from alpha i's by W, these are called real. And some you cannot obtain by W, and these are called imaginary. Okay. Very well. So so let me just make a couple of statements. So first of all, what I would like. One more important structure that we can have here is non-degenerate bilinear form on L of A. So it's also very important for structure theory of semi-simple algebras and hence for in here. So so important class of generalized Cartan matrices is symmetrizable. So I assume A is symmetrizable. Okay. So A equals to D. So what it means? So that is, it's like that, where D is a diagonal matrix, Dn. And here, D, without loss of generality, we can actually take Di to be greater than 0. Why without loss of generality? It's a statement, and which should be proved, but let me just state it, okay? And then B is symmetric. So what are analogs of DIs in the semi-simple case? So you should think of them as this number 2 over alpha I. Because, and B, ij is alpha I, alpha j. Right? So if you multiply this diagonal matrix such enters on Bij, you will get Cartan maxes that we're used to in semi-simple algebra case. Then I can introduce. So this is kind of, motivation. Then I introduce motivation for the following. Introduce form on a linear real span of pi check. It's not the whole H star yet. So we have alpha by the following: alpha I of alpha j. Of course, I would like it to be AJI over DJ. Right? When we have this picture, it's kind of natural why we would like to do this. So it's definition in our case. So and we can introduce also form on linear real span of pi. In a similar way, you just take HI, HJ, and this will be alpha I, so the form on alpha I, alpha j times DI times DJ. And this is also consistent with what we had. So a theorem that can be proved using what's called grading on L of A is that so theorem, so that the form extends to symmetric bilinear invariant form on the whole L of A. And this is an important instrument in here. And actually you can check just using our definition of Weyl group. Quite small. So this, of which one? Of this one? So this is J I. This is J. And also, you can check just in straightforward way that this is invariant with respect to the action of Weyl group. It's just straightforward check using our definition. Okay, and definition actually of form. With this definition, actually, lambda of hi becomes to what you need. Yes, for simple roots only, not for other roots. It's hard. Like for other roots, you don't know actually if it's the square of its norm, if it's positive or negative. So now, statement that I wanted to prove, but I don't have time, is that alpha, root alpha is imaginary if and only if alpha alpha less or equal than 0. So that's where the whole, that's why they call it imaginary, first of all, right? The square of a root actually can be negative, right? So for real roots, this is positive. For imaginary, that is negative or can be 0. So now example next time for SL2 hat, for affine SL2. You will have like a bunch of imaginary roots, but they all will be what's called isotropic. They are orthogonal to themselves in a way. So this will be 0 in our example. But okay, this is not hard, not very technical to prove. Just need some additional look at imaginary roots. Another very interesting result that I would like to state, so you just know, and we will see this on an example, what can happen with how imaginary roots behave. Actually, so another proposition is that suppose alpha is an imaginary root, then k alpha is also an imaginary root. This is for all k from z without 0. So all integer multiples of k are also imaginary roots. So whenever you found an imaginary root, like this never happens in finite dimensional case, right? Then like all the multiples is also roots. So, and we will see an example of this. It's like that's where like this affinity comes. This you should think of this root sometimes like in affine algebra as like a shift, right? So you have like an additional structure which is this shift, and you can apply it a lot of times actually. And we'll see that in formulas. We'll see that next time. Yeah.
Is this clear by this property?
No.
So the form is not linear?
It's not clear if I take alpha, multiply by k, and I still will be in root system. This is very not clear. So I'm saying if I take alpha and I already know that it is a root, then this is the thing. Yeah, so if I take alpha, no, it is a root, and alpha less or equal than 0, then I say it's an imaginary. But here I don't know if k alpha is a root actually, and this is very surprising that it is a root. Something which does not happen in finite dimensional case. And this one is actually much harder to prove. Still we can do it like in a quarter of lecture, I think, but much more technical than say this. So what?
What is the book?
Yeah, so the standard book is Kac's book, Infinite Dimensional Algebras.
The same name with Kac-Moody.
Yes, yes. So he himself wrote this book, and it's pretty good book, very consistent. Yes.
It's a recent one?
What?
This Kac-Moody algebra is more recent one?
So the question, is it recent?
It's, yeah, like these things.
I think it's 1991, so already 30 years.